Hello, class. Welcome back to EE415. It's been nearly a month since we actually saw in class. I hope you guys had a satisfying midterm week, although this course did not have midterms. So I apologize. I'm feeling a bit under the weather. I don't think I could manage to actually be in class in front of you today. So I'm going to record the lecture for you guys to view and understand. And as usual, if there's any questions you might have on the contents, just post it on Campus Wire, and the teaching staff will address it as soon as we can. So so like I said, it's been about a month. So I don't know if you guys still remember the last time we met. We talked about, the paging, the size, the page faults. If it's not in memory, if the page is not in memory, you need to go grab it. The first part of today's lecture is about, policies. So basically page replacement policy. And we have done something similar when we talked about scheduling. But this is going to be the last piece of the first part of the whole textbook. If you remember, textbook's name is 3 Easy Pieces, and the first part is the virtualization. And this part will be the last section of it. So this part is all about how to decide which page to evict, so page replacement. So this decision is obviously, you follow some principles. But as you will see, section algorithms has some corner cases, so there might be some tweaks to avoid those behaviors. So the goal of the cache replacement algorithm is basically to minimize the number of cache misses, right? Miss is bad, because if you miss it, you already wasted time. Now you have to go grab it on the disk. And even a single miss actually incurs quite a bit of overhead. So we need a metric to evaluate the effectiveness of the replacement algorithm. And for that, we have something called AMAT, average memory access time. So this has 3 components. So first is T sub M, which is a cost of accessing memory. Now, the other part involves P sub miss, percent miss rate. So basically, cache miss rate, right? And this varies from 0 to 1 and multiplied by T sub D, which is the cost of accessing disk. Now, if there is a miss, you go grab it here. And if there's, if it's a cache hit, you just do this, right? If this is 0, then you only have this. Now, keep in mind, if there's a miss, you go grab it from the disk, and then you have to also access the memory, right? So that's why AMAT equation basically looks like this. So let's think about what will be the optimal replacement policy. So the optimal case, obviously, you want to have fewest misses. So then when we do the replacement, how can we know that we'll have the fewest miss? So the basic way to do it is to replace the page that will be accessed furthest in the future, right? If it's not going to be used for the longest time, you get that page out of there, right? Because we're not going to need it for a long time. If we're going to need it soon, you want to keep it in there. Now, obviously, in real life, future is hard to predict, right? So this is difficult, if not impossible, to implement. So we're going to use this optimal replacement policy only as a comparison point, right? So how is my policy as close to the optimal replacement policy? You cannot beat it, but how close can we get? So for the optimal policy, let's use an example. So this is the axis. And let's say we have three available pages in the cache. Now, let's say initially there's nothing, right? The cache is empty. So since we have three spots, first three will end up in a miss, right? Meaning first three different item accesses. So these are misses, all misses. And after each miss, these are all added to the cache, right? So the misses at the initial phase, right, where there's no items in the cache, we call that cold start miss, right? There's nothing you can do about it. When you start, you need to have it, right? So this is unfortunate, but can't avoid it. So some people, when they actually calculate the hit rate, which we'll talk about just a little later, they could elect to actually remove these cold start misses. Anyways, now we have the cache of 0, 1, 2. The next one is 0, and we have it. Awesome. It's a hit. Next one also 1. It's a hit. Now let's say the next axis is 3, and here this is 0, 1, 2. Right? So this is a miss, unfortunate. And now we need to evict one of 0, 1, 2 and replace it with a 3. So now the question is, which one do we kick it out, right? So this is optimal, right? Where we have a crystal ball and we know the future, right? And now we can see here among 0, 1, 2, there's 0 and 1 in the near future of axis. So probably better to evict 2, right? So now we see 3 instead of 2. Moving on, now 0, we have it, so it's a hit. 3, we have it, it's a hit. 1, we have it, it's a hit. 0, 1, 3, but now it's 2, so this is a miss. Now, so between 0 and 1, yeah, if I'm on 0, 1, 3, right? Which one do we evict, right? So in the future, we know it's 1. So as long as it's not 1, we'll be okay. So either 0 or 3, we're fine. So here we just kick 3 out. So 0, 1, 2, and 1 is a hit. Okay, so hit rate is basically hits divided by hits plus misses. This case, including cold start miss, optimal still only 54.5%. So that's the optimal policy. So let's go through a few policies, starting from simple ones. The one we know well, FIFO, first in, first out. So basically, pages are placed in a queue when they enter the system. And when the replacement needs to happen, the page on the tail of the queue, so basically the one that got in first, will be kicked out. Obviously, very simple to implement. But here, we cannot actually realize the importance of blocks. Not all blocks might be equal, but here is just order, right? There might be pages that gets accessed a lot, right? But you can't actually put a weight on this, right? It's easy, simple, but most cases not very effective. So again, let's trace using FIFO this time. So again, these are cold misses, but first in 0. So yeah, so these are the top of the queue, right? And this is bottom of the queue. We have 0, 1, 2, 0 comes in. It was a hit. 1 also hits. Now, we got a 3. We don't have a 3 here, right? So here the first stand was 0. So you simply kick this out. Now 1, 2 moves forward, and 3 now enters the queue. Unfortunately, we kicked out 0 based on first stand, and now we need to access 0. So this is a miss. So again, following a policy, 1 was the first stand, so it gets out. 23 moves forward. Now 0 enters back. 3, fortunately, we have it. So this in. 1, again, we just kicked it out. Sorry, but that's how it is. So again, now 2's out, 3, 0, move forward, 1 comes in. And then now we want access 2, which we just kicked out. So you see the point here, right? This sucks, right? So at the end of the day, the hit rate was 36.4%. There's another simple one, which is random. So we just pick a random page to replace under memory pressure. So you have some random function, choose something. It's very non-deterministic. But again, very simple to implement. And again, you can't really put an importance of block here. And you're not trying to do anything very smart. This simply depends on, pure luck. So sometimes it actually does well. Sometimes its performance is close to optimal. And sometimes it's really bad, right? Because it's random. It's based on luck. So yeah, we're not going to go through traces for that, but instead, let's do something that's being used a little more widely. So principles of locality. So we're using history to guess the future, right? It's hard to know the future. So when we have to guess the future, we typically rely on historical data, right? Yeah, people who have done well tend to do well in the future as well, or you see some trends, right? So there are 2 types of locality we can utilize. First is frequency. So if a page has been accessed many times, so if a page has been accessed frequently, this should not be replaced, right? Least frequently used. The other is recency. The more recently a page has been accessed, the more likely it will be accessed again. So that would be LRU, least recently used. Let's dive into LRU. So again, same access pattern. So first 3 core misses. Now 0's a hit, 1's a hit. But now 3 is a miss. Now, we're actually, yes, so we're going to actually order the cache state here. So basically the right-hand side, yeah, is the most recently used. So the least recently used item will be on the leftmost side, right? So when we have a miss, 2 had been accessed least recently, right? So 2's out and 3 goes in here. Next, 0 is a hit, and you move 0 into the back because it's just recently been used. 3 is a hit, now goes to the back. 1's a hit, also goes to the back. 2, excuse me. Unfortunately, not in the cache. So here, the least recently used item was 0, so you kick it out, and 2 goes back in. Next one, 1, it's a hit, right? So as you can see, this is doing much better than things like FIFO. Now, when we're trying to evaluate these policies, we need to consider the workload, meaning, what is the access pattern, right? What is the behavior of which page are being accessed, right? And again, we can use some kind of history to come up with these, but let's go through some example ones, typical example ones. The first one is no locality, meaning basically everything is random, right? So here, let's say the workload accesses 100 unique pages over time. Now here, Y is a hit rate. X is actual cache size. So obviously, if your cache size is 100 for 100 unique pages, you don't need a replacement, right? So everyone will be good, right? Everybody gets a hit rate 100%. Now, when there's no locality, the bottom line here is obviously the optimal, you cannot catch it. Other three are basically the same. So it doesn't really matter, right? So if it's basically random, your replacement algorithm really doesn't matter, right? So here's another thing, right? Because you can't not foresee the future, these kind of performance would happen, right? Now, the next workload we want to consider is a much more realistic one, which is called the 80-20 workload, right? So what this means is that 80% of the references are made to 20% of the page. Okay, so majority are accessing, to top 20%, top 20 popular pages. For the remaining 20, the references are made to the remaining 80% of the pages. So as you can see, optimal obviously the best, but now LRU rises with a much better performance than FIFO or random that does not use any historical data. Yes, 80-20 is you might have also heard like companies like Google. I don't know if they still do it. They said 20% of the time, or let's say one day of the week, you should not work on your current project, but you should instead spend it on exploring new topics, future projects you might want to work on, right? So while you still committed to delivering your current assignment, you always have to look out for what's next. And, they encouraged you to consider 20% of the time for that. Anyways, yes, I digress again, but that was the 80-20 workload. The next one is called the looping sequential workload, where you refer to 50 pages in sequence. Basically, you start at 0, then 1, 2, 3, up to page 49. Then we loop again, 0, 1, 2, until 49. For a total of 10,000 accesses, 50 unique pages. Now, one might wonder, why is this even realistic? Well, a typical example are like the database applications that actually do it. So here are obviously 50, right? If you look at here, so if you just go one by one, LRU sucks, right? Until you hit 50, then all the algorithms would achieve 100%, right? So in this case, even these random actually even does better than LRU. So this is the corner case where LRU actually doesn't do well, right? So when you design or select algorithm, you need to know the workload. So that's the takeaway message. So LRU, most cases, is the winner. So let's think about implementing this, right? Now, to realize LRU for each items, we need to track when was the last time it was used, right? So you have to keep track of that. for every single one. And if you have to evict something, you even have to scan all of them. I mean, think about a very large system, right? Where there's many, many, many pages, right? So this could be very, very slow. So do we actually have to strictly implement LRU, or can we actually approximate it, right? So the answer is yes, but we're going to need a hardware support in a case of a use bit, or some people call it a reference bit. So whenever a page is referenced, this bit is set by the hardware to 1. Now, although hardware sets it, it never clears it. So OS actually clears it. So let's look into an example of this, which is called a clock algorithm. So here, all pages of system arranged in a circle list. Let's say, like, we have, this is a bad looking circle, but you get the idea. So then you have a clock hand, right? Like a clock. Let's say clock hand points to some particular page to begin with, right? Now, again, now we need to evict something. We're doing LRU. We need to evict, approximating LRU. Now, if currently pointed page has a use bit of 1, it means it's been recently used, right? So you don't want to evict this, right? So when this happens, OS actually clears it to 0, right? And then you move forward. So now you're looking at the next item. So this continues until it finds a use bit that is set to 0. So this could be either this item has not been recently used, right? So you evict that page, or let's say all the pages have been recently accessed. Then, if you remember, as the clock hand goes around the circle, we clear it to 0, right? So as everything's 1, hey, we have to pick something, and whichever clock hand was pointing to, sort of random, but you evict that, right? So that's approximating LRU. So going back to the 80-20 workload with the clock, so there's LRU and there's clock, right? So very similar. So obviously clock is not as good as the perfect LRU, but still much better than the non-history algorithms. So much easy and efficient to implement, and performance, not that bad, as good, not as perfectly as good, but as good as LRU. So that's good enough, and the trade-off that's worth making. Yeah, one more thing, dirty pages. So there's something called a dirty bit or the modified bit. So if a page that's been modified while in memory, right, then it's dirty. Now, when you're trying to evict it, this must be written back to the disk. So certain algorithms might actually prefer the clean pages, right? Because the eviction is actually free, right? So you could consider dirty pages in your replacement policy. So other than replacement, there are other things in the virtual memory. So one is page selection. So this involves when to bring a page into the memory. And the two represented, one first is demand paging, which basically involves OS bring the page into memory when it is accessed. So on demand, when there's a demand, when this needs to go into memory, then you do it. Or I want to be a little more efficient. I'm taking a risk, but I want to be efficient. you guess the page that is about to be used, and you bring it ahead of time. So you want to be damn sure this is going to be used. And, considering the workload, you might know, hey, this is almost sure, almost perfectly sure that this would need to be fetched. Then you do it ahead of time to reduce the time to actually access it. So that's prefetch. Now, when you're writing pages out to disk, if you do it one by one, that's not very efficient, right? So typically we do clustering, or you could just say this is a grouping of writes. So you collect a number of pending writes together in memory and write them to disk in just one single write. Yes, yeah, I just said one last thing, but this is the real last thing. Thrashing. So basically, memories oversubscribe, meaning the demands for memory of the set running process simply exceeds the available physical memory. So then what you want to do is you decide not to run a subset of processes, right? You can't just satisfy everyone, right? So you basically do admission control, right? So the reduced set of process working sets, fit in a memory, and yeah, so you can't just take everyone in, right? So same as like in a indoor room, there's a limit of people that can be in at the same time, because if you have more people, that's dangerous. Same in systems. So that's thrashing. Yep. So that's the end of the first part. I will meet you for the second part of today's lecture.